software engineer at heart, but somewhere along the way, I got a PhD in artificial intelligence. Okay, so that took me on a different track, where I ended up working in areas like machine learning, data science, data analytics, computer vision, and robotics. Right, and then I've been in Thailand as an academic since about 2004. Okay, and so currently I'm the head of the ICT department at the Asian Institute of Technology and also the director of the AIT Artificial Intelligence Center. So what we're trying to do is to take innovations like in artificial intelligence and machine learning and robotics and then turn those into solutions that can solve problems here in Thailand or the rest of Asia. Okay? And then another thing that happened along the way is I started a company with a colleague at AIT, and this company is called Pineapple Vision Systems. Okay, so the goal of this company is again to turn AI technologies, especially in kind of video processing and image processing, into products that can help solve problems here in Thailand in particular. Okay. So this is my background and what leads us to the talk today. Well, so we're trying to build software that is made in Thailand, but is customized for the Asian situation. Okay. So what we end up doing is we try to build systems that use innovative AI technologies. Okay. But then we want to make those technologies as practical and low cost as possible. Okay, so take for an example video processing. Okay, so suppose you have an edge device like a video camera, right? And what you'd like to do is get some useful information out of that camera, right? This could be about vehicles, it could be about humans, anything that you're interested in tracking and observing using video cameras. Well, if you'd like your software to solve the problem, when you have a high bandwidth stream of information coming in, you cannot stream video directly to your servers in the cloud, at least not today. Maybe soon with 5G. When will 5G be here for us in Thailand? Maybe? Okay. Anyway, let's see. Okay, so anyway, in the meantime, what it means is that if we want to do some high bandwidth processing, we have to put it close to the end user device. Okay, so that's called edge computing, or when you mix edge computing with cloud computing, this is what people are calling fog computing, right? This hybrid solution. Okay. So some of the applications we work on would be, for example, traffic monitoring and law enforcement. So I'm sorry to say, if you've gotten a ticket, a traffic ticket from an automated system, that's probably our software that issued that ticket. So I apologize, but anyway, we hope that we're doing some good to improve the traffic situation in Bangkok and other places in Thailand. So yeah, we have a Thai license plate recognition product for access control for vehicles and so on, and we're working with businesses and using video analytics to improve their business intelligence as well. So anyway, yeah, so we're stuck with this fog computing model for the time being. Okay, so these AI analytics that we develop, they take a lot of time and effort and money to develop these systems. Okay, so if we're going to turn this into a commercial product, then we would like to maintain our business advantage as long as possible. Okay, so if we're taking our software that's doing this intelligent processing of data from edge devices, okay, and we're putting it in these fog nodes. Well, where are these fog nodes? Well, in our case, we have a bunch of fog nodes, if you can call them that, deployed across the city in things like police boxes at junctions and intersections in Bangkok and other cities in Thailand. Also local police stations, also a retailer, if you're processing data at a retail shop, then the server is right there in the customer's hand, okay? So what that means then is that your customers then, okay, maybe not the customer, but someone the customer knows, becomes an adversary, right? That you want to prevent them from taking your software and using it in a way that they didn't, is against the contract, is against the license, or is against basically trying to steal and copy the software. Okay? All right, so now that's why I want to talk about software licensing. Okay? So we would like to take our software and hand it over to the customer, right? But with some conditions, that they can only use it with one computer or server, or that they can only use it with one end camera or other device, right? Okay, so this is the situation. So the customer sends some money to us, right? And then the software engineer sends back a program, right? So the customer installs the program on their server, right? And then the worry is that, of course, that various adversarial situations, they could copy the software, they could run it with more devices, they could run it longer than we agreed, right? Anyway, any use of the software that goes against the contract that we sign with the customer. All right, so probably some of you have been in this situation already, right, where you're somehow selling software to an end user, right? So we all face this situation. So until recently, there were a few approaches to solving this problem, but they're not very satisfactory, right? So the first thing that you might do is put some kind of blocking instructions into the software, okay? And what do these blocking instructions do? Well, they would check some condition, right? Check if the license is valid. You might have a verification code that needs to be entered by the customer. You might take a fingerprint of the hardware on the system, right, and store that and check that fingerprint every time the program starts up. Probably for a lot of enterprise software, right, you would put something on a hardware dongle that's required for the software to start. Okay, so what's wrong with that approach, right? Well, it's not that difficult, right, for an adversary to then, okay, if it's a verification code situation, maybe they can just guess the code, right? The software's right there, maybe on your hard disk, right? So you can do a dictionary attack against this code fairly straightforwardly. If it's a hardware dongle, right, you try to bypass the dongle. And of course, if it's a simple, non-obfuscated check in the code, you can do some very simple things, like run the code in a debugger and see when it's checking the license conditions and just bypass those instructions. I remember I used to try to do this when I was in high school, right? Trying to break the copy protection on games, right? So even a kid can do that kind of reverse engineering. Okay. So another way that we have is, okay, it's in a way it's the same principle, but let's make it more complicated, right? So if there's blocking code, where you just make it more difficult to determine where that blocking code is, right? So we obfuscate the code. Or another way would be maybe we obfuscate the code in order to somehow protect the secret, whatever is that intellectual property that is embedded in that code. Okay, so you can think of lots of different examples that might use obfuscation to try to protect the software. Okay, so what can our adversary do in those situations? Well, again, so it's really the same process of reverse engineering, right? No matter how much you obfuscate, if you're going to make the software runnable, right, on the end user system, then there's some theoretical result that actually, in general, this code obfuscation task is actually impossible. You cannot obfuscate code against a very resourceful and dedicated adversary, right? Okay, so so we're kind of stuck, right? Theoretically, secure licensing, right? Actually making sure that the license the contract that you signed with your customer cannot be enforced, right? So what are you going to do if your goal is to sell software that is being held in the customer's hands? Okay, so we're going to try to address this problem in this talk. Okay, so fundamentally, what's going on here is that we're trying to run protected software in a hostile environment. Okay, the hostile environment, it really could be anything. It could be attacking or trying to subvert the license conditions that we have put in place, right? So we love the operating system, I/O network, right? So actually, this program that we're running is, in a way, surrounded by the enemy, right? When the system is in control is not in your own control. Okay, so this comes up in fog computing, as I already mentioned. Another case where this comes up and could be a concern in some cases would be just whenever you outsource computation on the cloud, right? As Professor Asokan was talking about this morning, right? So lots of situations where you want to run your software in somebody else's hands. Now, if you trust Amazon or Microsoft or Google, right, then maybe this is not so much of a concern. But then, of course, as we move to more distributed hosting situations, then again, it becomes a problem. Okay, and of course, some people don't trust Amazon or Google or Microsoft either. Okay. Anyway, so the solution, or one possible beginning of a solution here, the same approach that Professor Asokan was talking about this morning, right? And so that's the idea of a trusted execution environment. Okay, so so in a way, he did half my work for me to explain in Intel SGX already. So anyway, I'll just give a quick overview of what are the properties that a trusted execution environment should be able to give us, right? So first of all is integrity, okay? When we deliver our program to be executed on the client's system, we would like to guarantee that the program runs correctly in the way that it would run if it was on a system under our own control, okay? So we don't want anybody to change the code. Confidentiality. Okay, as the software is executing, we don't want an attacker to be able to reverse engineer what the software is doing, right? Or otherwise get access to the results of the computation. Okay. Then finally, confidentiality of the result or the computation itself, right? So any intermediate result also we would like to keep secret during execution. Okay. So how can we do this? Well, these are the properties that a TEE should be providing. Okay? So, all right, so we want a TEE. Now, Intel has developed this thing called SGX, and they claim that this provides these capabilities. So let's take a little bit at things from the software engineering point of view, right? How do you actually develop a program that uses SGX? Okay? So it looks like this. So any program that you develop, right, at runtime is going to execute as one or more processes on one or more systems, right? So when you actually create an executable that you're going to run on some system, right? Then you've got the main executable, you've got some maybe shared libraries that are linked with that executable, and so on. So when you use SGX, the segments of your program are going to be broken into at least two kinds, right? The trusted code and the untrusted code, all right? So in SGX terminology, the name of these trusted segments of code, these are called enclaves, okay? So now, I don't do Windows, I do Linux when we do this kind of stuff. And so on Linux, at least, these enclaves, they come in the form of Linux shared libraries, okay? So the shared library is going to be loaded into memory dynamically by untrusted code at execution time. And then Intel SGX will take over executing that segment in a trusted way. Okay? Yeah. So, okay. So that means we have both trusted and untrusted code that's running as part of the same program, right? So you might start maybe your main, and if you write C code, right, your main is in this segment called P1. Okay, so it's executing on the processor, and so that process during untrusted execution can do anything, right? Anything that the user executing the program is allowed to do, like execute system calls, talk to the kernel, do network access, whatever, right? Okay. So so the trusted code, however, when it runs in the trusted environment, it's not going to be able to do some of these things like make system calls and perform I/O. So this is my take on what trusted code can and cannot do. Okay. So when we're in untrusted mode, then your program can do just about anything, right? So your main is always going to be untrusted, right? But in SGX, what what they provide to the developer is this idea of an e-call. Okay, so an e-call is the interface from untrusted code to trusted code. So in a way, your shared library that implements your enclave, you can think of it as being a kind of an API consisting of several e-calls that untrusted code can execute, right? Okay, so when we make these e-calls, then the processor will switch to trusted mode and do a lot of things to verify the integrity of the code that's executing. Okay, so trusted code. So it cannot make system calls. Okay, so any kind of I/O that you want to do, right, or access to devices on the system will have to be done through untrusted code only. Okay, yeah, so you cannot have a main. So the program itself is encrypted, right? So each page that contains code is encrypted, and as Professor Asokan said, right, is only decrypted when it's loaded into the processor. Okay, so besides that, your enclaves have access to some secrets that are actually provisioned by Intel at the time that the processor is burned, right? Okay, so you can return to untrusted mode, however. You can execute system calls, but you do this through an interface called an O-call. Okay? So SGX is all about you implement your E-calls, and then you might make some O-calls as well to leave trusted mode. Okay, so we'll talk a little bit more about the programming model here. Okay, so I already mentioned what is an enclave. Okay, so it's a program, right? So in this case, we take this segment called P2, okay? The enclave itself is not only the code, okay, but it's going to be the public key of the service provider. Okay, so in Intel language, the service provider is the software engineer that made the enclave. Okay, so in addition to the public key of the service provider, then we're also going to ship with this enclave a signature. Okay. The signature is generated with the secret key of the service provider, and it's signing these three things. So what are these three things? And actually some other metadata that are not so important. So what's MR Enclave? MR Enclave is it's basically the signature, or it's a kind of a summary of the contents of the memory. Once the program is actually loaded into memory, okay, and then MR Signer is the information about the service provider. Okay, so you've got information about the enclave, and you've got information about the service provider. Okay, now one of the things that we would like to do besides ship an enclave, so I should mention that an ordinary enclave, when we ship the code is just sitting there in the shared library and is accessible for anyone who wants to reverse engineer it. So if you also want to protect the intellectual property that is implemented in that software, then you need to protect the code itself, right? So then in order to do that, you need what's called an encrypted enclave, okay? So an encrypted enclave is shipped in the same way as an ordinary enclave, except that the code segments and the data segments in the shared library are encrypted. Okay, so then how? Okay, then they're encrypted. Then how are they going to get decrypted? So we'll talk about that in a bit. But anyway, yeah. So the encryption of the enclave is done with some secret key. Okay, so we'll talk more about what that key might be. Okay, so we're talking about another segment here, perhaps P3. Okay. And so then we're also going to provide in that along with the encrypted code, we're going to include things like the public key of the service provider, the signature of the information about the enclave, the information about the service provider, and so on. Okay. All right. So just to remind or introduce, if you're not familiar with some of the building blocks that we need in order to build up the system. So a digital signature, right, uses asymmetric encryption, right, or asymmetric cryptography, right. So we have two keys: the secret key and the public key. Okay. So we can sign any data with the public key or the secret key. The secret key, right? Okay. So some of you are listening. Good. And then of course the signature can be verified by anybody using the public key, right? Okay, so that's the digital signature. Okay, so we're going to provide these along with our enclaves, right? Okay. Now, another building block that we need is symmetric encryption, right? So here we have two people sharing the same secret key, right? Both for encryption and decryption. Okay, so we need both of these in order to build up this solution. Okay. All right. So this when we take a code segment P and we make it into an enclave, and these are some of the things that SGX offers to us. Okay. So first of all, we can ensure the integrity of P. How do we do that? Well, we can take the signature that's included with the enclave, and then we can verify that signature just using the information in the enclave itself and the public key of the public key of the service provider. This, of course, assumes that you somehow have some way to get the public key of the service provider, but in SGX, that's actually embedded in the enclave library file itself. Okay, so it's provided as part of the enclave. Okay, what else? So we can keep the memory contents during execution of P and its outputs confidential. Okay, so that's another thing that we need. Okay, but unless we actually verify the integrity of the enclave that's executing, right? We don't know if it's our enclave or somebody else's enclave that we might be talking to, right? So that requires this idea of remote attestation, which Professor Asokan also talked about this morning. Okay, all right. So these are the building blocks that we need in order to do secure licensing. Okay. So how do we do that? Here's the idea. Okay. So the customer sends money to the software engineer. Now the software engineer is going to send back a program. Okay, and this program is going to consist of some untrusted code and some trusted code in the form of enclaves. Okay, the key part of this program is going to be encrypted, right, in order to protect the confidentiality of the code itself and prevent reverse engineering. Okay, we're going to encrypt the code with a symmetric encryption algorithm. Okay, so that means that what the engineer your DevSecOps pipeline needs to use the same key to encrypt this code that the customer is going to use to decrypt it. So this is one of the problems we have to solve: is how to get that key to the customer's premises safely. Okay. Yeah. And so then, of course, the goal is to prevent our attacker from doing bad things with that software and violating the license in any way. Okay. So yeah. So we're going to encrypt the program to keep it from being shared, okay? But now this is the issue, right? We want to let the customer decrypt this program and execute it without being able to, share that key with an attacker in any way. It seems quite difficult, right? Yeah. So the idea then is that we're going to make the software decryptable, but only when we're in trusted mode, okay? So, and then we're also going to make sure that this key is only available in trusted mode and never leaves the memory. Okay. So for that, we need another primitive that's provided by SGX, which is called sealing. Okay. So using those basics, right? Let's see the different stages of this process. Okay. So the first step is purchase, right? So however you sell your software, right? This depends on your particular application and your sales pipeline, right? So when we buy the software, right, we're going to get the software and we're going to get some kind of secret that we can use just one time to activate the software. Okay. So on the very first time that we run on the system, then we want to activate the license. Okay. So at that time that we activate the software, then we're somehow going to get this secret key used to decrypt the other parts of the program, right, in a secure way. Okay. Then later, actually, so this is something that, if you think about it for a moment, you see, oh, okay, maybe we can do this once, but remember what Professor Asokan was talking about this morning, right? You don't want to go through this complicated remote attestation process every time you run the software, right? So that would be a real disadvantage if we had to do that. So what we'd like to do is have kind of a lightweight reactivation process where we can activate the software again and again and again using that same decryption key, but presumably stored in a safe place. Okay. So, to see how this works, right, we're going to start with the reactivation part, right, because that will help you to understand why the pieces that are here in the activation part need to be there. Okay, so here's the reactivation process. We want to take this encrypted enclave and we want to run it on our TEE, right? So how are we going to do that? Well, so our untrusted code is going to bootstrap the process by calling it's part of the Intel SGX SDK, the SDK that they provide for development. So they have a fancy procedure called load encrypted enclave. Okay, so load encrypted enclave requires a couple things. It requires the actual enclave that you want to load, which is encrypted, and it also requires a sealed decryption key. Okay, so the decryption key is going to be stored just in a file on the system, right? But that key will only be decryptable using the unsealing key that is tied in with Intel's keys that were provisioned at the time that the processor was created. Okay, so we have to call this function called load encrypted enclave. Okay, so U is going to do that. All right. Okay, so then now that you kind of get the idea, right? This is the reactivation procedure. Right? We talked about reactivation. So now we know that we need to have a key, and we must be able to seal that key. So somehow we have to get that key. So now let's talk about the registration process that needs to happen before activation. Okay. Yeah. So this is what needs to happen. So first of all, the seller is going to generate this the secret key, and use that key to create this encrypted enclave. Okay. Then what we're going to do is we're going to create an accompanying enclave called RE. Okay. So this is a remote attestation enclave. Okay. We also need to create some stub code that's going to start everything up. And then we provide this token that's going to be used to actually activate the software. Okay? So give all of these to the buyer, except for K-star, right? So we send the encrypted enclave, the remote attestation enclave, the untrusted bootstrapping code, and this token. Okay? Now, of course, you need to have some secure channel to talk to the customer in the first place, right? But presumably, as part of the same session where they buy the software, then you send them their activation token, right? Okay, just to make sure somebody doesn't steal it along the way and grab that license. Okay, so that's the registration process. Okay, we don't worry about that too much, right? We're going to focus now on the activation process. Okay. So this is how this activation process works. Okay, we're going to have a few parties that are communicating in order to get the job done. Okay, the first one that is executed is the untrusted code. So as soon as sometime after the customer gets the software, they run U. Okay, what does U do? It's gonna work on the client side with the remote attestation enclave. And another enclave called QE, which we'll talk about in a moment. Why is QE needed? Then it's going to interact with the service provider, right? Which is also going to talk to, and we'll see why this is necessary, this service called the Intel Attestation Service. Okay? So the service provider and the Intel Attestation Service are going to work together to attest this enclave is executing on the client side. Okay, so how do they do that? Okay, so U is going to activate RE. Okay, so RE has hard-coded into it the public key of the service provider and has associated with it the token that was given at the software purchase time. Okay, the service provider, in the meantime, has, of course, its public key, its secret key, and then also the public key will establish a shared session key, and then that shared session key can be used to generate additional keys as needed for this process. Okay? Next, the remote attestation enclave and QE are going to generate a quote. Okay, it's called a quote. All right? This quote is what's going to be used by the service provider and Intel to say that the code running on the client is legitimate, it has not been modified, is an enclave, and is also running on an SGX. Okay? Now what is this QE? It's called a quoting enclave, and this is part of the SGX platform services. So what are the platform services? This is the necessary software that's installed on the system at runtime in order to facilitate any operations that use SGX. Okay? This enclave it's another Intel SGX enclave, but this one is written by Intel itself. And of course, that means it's signed by Intel, right? And is supposedly an enclave that we can trust, right? Okay. All right, so after the code is generated, it'll be sent to the service provider. Then the service provider will work with Intel to verify that this enclave RE is indeed our RE and is running on a properly configured SGX platform. Okay, so what else? Now we're trying to check a license. So the last thing that we have to do is, on the service provider side, is check that the user is actually paid, that this token is valid, right? And so then and only then will they send the decryption key back to the RE. Okay? At that time, then RE will seal the key. Okay, so we will encrypt the key so it can be stored on the disk safely, right? And can only be decrypted later by RE or one of its friends, right? Basically other enclaves that were developed by the same service provider. Okay, it's a little bit complicated, right? Okay, all right. So now, so there I've talked mostly about the kind of the software engineering and the communication that needs to take place in order for this to happen. So now with my colleagues who are security and cryptography experts, what we realize is that actually this idea of remote attestation with key exchange and secret sealing, it's a kind of complicated primitive, but it's a new primitive for cryptography. Okay, so we'll look in a bit more detail at how it works. Okay, so the first thing that happens is a Dippy-Hellman key exchange, right, to establish this shared key, right, that the two parties can use to communicate. So what this means is that the operating system or any untrusted code is not going to be able to get any information about the communication that's occurring between SP and RE. Okay, so this key is since the key is generated inside of SGX, right, and as long as Intel is doing its job properly, then the other elements on the system cannot get access to this information. Okay. All right. What happens next? So RE first asks for an E report. Okay. So this is a instruction that's now part of the Intel the Intel instruction set, right? That actually will do what? It will run a report on the currently running enclave. Okay, so RE asks the processor in trusted mode for a report of itself. Okay, so this is called a report. It has things like some hash of the memory contents for this particular enclave, and other things that can be used to verify that this what are the contents of this enclave. Okay, so now the report is tied to the current session, right, between the service provider and this remote attestation enclave, and it's generated for QE to be able to verify. Okay, so when you generate a report, you have to say, who is this report for? This report is for QE. Okay, so QE can then verify this report. Okay, and then it generates its own report So the quoting enclave also has to generate its own report, okay? And it's going to generate the report for RE. So now QE is actually doing a local attestation of its own validity to RE, okay? So now, at this point, QE believes in the contents of RE, and after RE receives this report, then it will believe in the validity of QE. Okay. Then in addition to that, it generates what's called a quote. Okay. So this is basically it's basically a collection of information about RE, right? That can then be verified by not by SP unfortunately, but by Intel. Right? Why? Because the quote is going to be encrypted with the public key of the Intel attestation services. This is another thing that's hard-coded into this quoting enclave. Okay, so the quote is this encrypted collection of information about RE. Okay, we send that back to RE. So RE is going to verify the report of QE just to make sure that that it's not going to send. It hasn't been, it's not communicating with a bad QE, right? Then finally we send all this back to the service provider, which then forwards the quote to Intel and asks, Intel, is this quote okay? And then Intel will send back a report of all the properties of this platform. Is it up to date with all security patches? Is the quoting enclave, is it legitimate? And is this RE, does it, all that information will be given in the report coming back from IAS. Okay. All right, so at that time then, the service provider can then encrypt the decryption key for the encrypted enclave using the session key that's already been established, right? And then this remote attestation enclave will then seal this key for later use. Okay, right? So that's a little bit complicated. Luckily, so now, if you're not a security expert and you don't know how to implement all of these primitives yourselves, and don't have to worry too much, you should consult with somebody who's smart, right? But that's what I do. I'm not the smart one, right? But luckily, Intel provides lots of sample code that you can use to build up your solution to this problem. Okay? So this seems to solve the problem fairly well, but let's talk about some of the limitations of this approach. So first of all is Intel's track record with SGX. So Professor Asokan just told us this morning about some total breaks of SGX that have now been patched, right? But you have to wonder, how often is this going to happen, right? This SGX platform is so complicated, so many different places that it can be attacked that it's not clear how secure it really is. Okay. Another issue is that actually, as I told you, in my company, we're targeting desktop. I didn't tell you this, but anyway, we're targeting fog nodes, right? Oftentimes, in order to reduce the cost, we don't go with enterprise-grade servers, right? We'll actually deploy our software on desktop machines, like a Core i7 or i9 and so on. And so it turns out that Intel is dropping SGX on the desktop. Okay, so they're going to continue to support it on the Xeon processors for the foreseeable future, because that's their main goal is applications like cloud computing applications and things like that. So anyway, there's a little bit of worry that they're dropping support on the desktop. How long are they going to support this technology on the server class processors? Okay, and then also, right, Intel is here, right? So do you really want Intel to be knowing what you're doing, right? Maybe if you don't trust the U.S. government or other associates of Intel, right? Or if you're a criminal, right? Then you probably don't want Intel to be looking over your shoulder, right? So there are some issues here, right? But from our point of view, this is far better than the current state of the art, where all we can do is obfuscate, right? So at least we have some protection that all the hard work that we put into developing software won't just completely get ripped off and copied the moment we release it into the world. Okay. Yeah. So having hardware-based security solutions, right? So I think it's it's easy for, it's relatively easy for us to use, right? And it's probably pretty easy for you to convince your boss that we should invest in a secure hardware-based solution. So, as I said, we expect flaws to occur. Another thing is that, okay, we really need to understand these TEEs in a systematic way, and so I think there's a lot of work to do on the sort of theoretical side and kind of modeling side in order for us to understand what are the properties that we can expect from a TEE and how can we make use of them. Okay, and then of course, yeah. Also, if you're from the customer's point of view, SGX and TEEs might not be a good thing, right? You know, I don't see Richard Stallman in the room, right? But I'm sure you know of him perhaps, right? So he would probably say, you know, that when you buy software, you should own that software, right? You should be able to, you should know what it's doing, right? And if you're running on SGX, you don't know what it's doing. You should be able to change it. You should be able to do what you want with it, right? So definitely, it's not the right solution for every application and use. Okay, so this is our take on this technology. So if you're interested in getting started with SGX, then you can download the SDK. They have the SDK for both Linux and Windows. There's lots of resources for you to make use of. It's not the best documentation in the world. You have to kind of experiment with things, right, to get things working. So Intel provides a attestation service that you can use without registering in any way. So you can actually generate service provider keys and test your solution without too much trouble. But then there is a fairly serious process, what they call onboarding. So when you want to move to production, then you have to actually, you know, talk to Intel and tell them what is your product, right? And they'll schedule a call with you, right? And you'll talk to an Intel engineer, right? Explain what you're doing and why you need to use SGX. And if they agree, finally, then they'll give you your production keys. And yeah, so it's a little bit heavy in terms of dealing with Intel. But I mean, they make it easy. They're very responsive and things like that. They definitely want to see the technology being used, so they're happy to work with vendors. Okay. Okay, so then also, if you happen to be interested in AI solutions, right, that we can provide in the AI Center or Pineapple Vision Systems, then please send email to our business development manager so we can maybe solve some problems for your business. And then I'd also mention, I just want to put in a very quick advertisement for the programs in the IT. Okay, so I'm also a professor, right? And need to get information out about our programs. Okay, so actually, if you're interested in software engineering, we have programs in software engineering where we teach about DevOps and all these kind of technologies. We only have master's and doctoral programs, and the most exciting thing that we're doing right now is a new master's in data science and artificial intelligence. Okay, this is actually a European master's program that we are leading this consortium of 15 universities and companies that are working together to create this master's program. Okay, so international program, best European best practices, doing training in AI, giving you research experience, knowledge transfer from Europe, and internships. So I want to emphasize this one, that we have scholarships for Thai applicants, right? So if you know anybody that is interested in a master's degree in data science and artificial intelligence, please tell them about our program, okay? And so besides that, I want to pass out a flyer about this program, okay? And that'll be the end of my talk, right? That's the end. Thank you.
Okay. Okay, thank you for presentation from Professor Matthew, and I hope you enjoy the last session and น่าจะสนใจเรื่อง AI ขึ้นมาว่า เพิ่มเติมก็หวังว่าจะเป็นข้อมูลที่ดีโอเคนะครับก็อันนี้เป็นเซสชั่นสุดท้ายเดี๋ยวขอมอบของรางวัลวิทยากรก่อนนะครับ